the dais is Julie Turner, General Manager, Duke Energy.
Good afternoon, everyone. I'll start by just introducing Duke Energy and who we are. It is the largest electric power holding company in the United States with approximately $115 billion in total assets. It is a regulated utility, and we serve approximately 7.3 million electric customers in 6 states. And you can see our service territory up on the graph there, or the map. It is commercial power international business segments, and we operate in North America and Latin America, and we do have a growing portfolio of renewable assets. Fortune 250 company, and our stock exchange symbol is DUK. So I'm going to mainly talk about everything that is in the dark blue on the graph, anything that is east of I-77. As I was introduced, I'm the General Manager of the Duke Energy operations, which means that I have all the combined cycles in North Carolina and several of the simple cycles, so all gas operations. Several years ago, we made the strategic decision to invest in the combined cycle plants to meet our environmental regulations, to reduce our NOx and SOx reductions. And I've been really involved in that transition because I was a plant manager at our Lee coal plant that was retired and was a part of the construction of combined cycles. So from the boots on the ground and what the impact is to the employees, I do understand that pretty well. And so I'm going to talk about the operation in my region, and there's 2 plants listed here. I don't know if there's a corner here. I'm going to try. There. So this is one plant that we have in the Carolinas, and you'll see I'll refer to this as a enclosed plant, or its operations are inside, and this is an external. Sorry if I put drywall out there. But within my region, I have about 6,500 megawatts I'm responsible for. There are 6 combined cycles, 15 simple cycles, which are frame units, and then some peakers. And you can see the amount of gas that we burn in my region over 2014. So, you know, I think it's a lot, but I think this year it's going to be a lot more. So if you think about, we've heard some things about capacity of the combined cycles. The average for the combined cycles in my region was about 67%. Upwards to 70% capacity factor, and our pricing this year, we are about $9 a megawatt hour ahead of coal, our cheapest coal, so that's a pretty good place to be. And in addition to the gas, since we're talking about renewables, we are adding about 140 megawatts in my region as well. And some things that haven't been talked about too much is the number of resources you need to operate these plants. You know, we've touched on nuclear a little bit. For a comparable size plant, we need a 20th of the resources to operate for the same amount of megawatts. And for coal, it's about a third. And I won't talk a lot about the gas capacity usage for Duke Energy because my colleague Joe McAllister will speak to that tomorrow, I believe. But what I wanted to talk about is really how we're learning, growing, and always improving in the operations. I'll talk about some industry events that have happened and what did we apply in our business to ensure we don't have similar events. Understanding the impacts of shale gas. We've talked a lot about shale from a global, what does it mean to us, and price. But when you get right down to it, what's happening in the field and what is the impact from that? And then how are we analyzing performance from a business standpoint? So a couple of events, and these are not new, so I'm sure you've heard of them before, but just clean energy in Middleton and also ConAgra, which is in Garner, North Carolina, very close to where I live in Raleigh. And the Chemical Safety Board, when they describe both of these events, they use the term planned and intentional release of natural gas. And those are very important words, planned and intentional. So when both of these events resulted in fatalities. With clean energy, they were in the final stages of construction for a combined cycle plant, and they were blowing out their gas lines. And it was about 650 PSI that they were blowing out the natural gas when, for some reason, they had a spark that created an explosion. 6 people were killed and about 50 were injured. And that was common practice, planned and intentional. Everyone did it. No one ever had an accident before. Safe enough. It's pretty good. And then with ConAgra, again, it was planned and intentional. They were replacing or adding an industrial water heater. And as part of the purging of the new line, they were having some difficulties getting the hot water heater ignited. They thought that what they had is some air in the line, and so they continued to purge that line. So they were purging inside a building and didn't realize that they had natural gas accumulated inside the building. And there was a spark again that ignited the gas, and that industry event resulted in 4 deaths and dozens injured. So from those events, we've changed our practices, and I think these are commonplace. To my knowledge, I know we're not purging or using gas to clean out our gas lines. I don't know if that's commonplace across the industry, but we do not do that. We are, once it gets inside the plant boundaries, we use nitrogen, or we at least to put a buffer between methane and air before we do anything, any kind of purging. We have a lot of methane detectors on the plant site. There are a lot of personnel that came to us from coal plants, and it was, if you think about the generation that the coal plants were in operation, smoking in the plant was kind of commonplace. That's a no-no. I mean, just think about walking around with a cigarette in a natural gas plant. So there's a transition that had to occur there. With purging the gas outside, we ended up doing a full assessment of all our plants to look at our vent paths for whether it's a gas dryer or anything else, and where the top of that vent path would be. And if it was near electrical equipment, or if it was near a line off the transformer, we ended up having to raise our vent pipes. So, I mean, these seem kind of minor, but it's about taking a different look at your plant. We also introduced natural gas purge procedures using nitrogen. And so continuous use has a very specific meaning to us, which is it is a step-by-step procedure. You do not deviate. If you find a problem, you evaluate it through engineering. You have to get your management to sign off on that. And, it wasn't just the natural gas, but we also had a fatality within our own plants. And it was related to hydrogen. And you probably heard about this at our Sutton facility. And so it was the need to follow our procedures as they're written, as they're intended, and you do not deviate. Because one of the things that happens is you get this sense of, if you skip one step and it makes the job a little bit faster one time, and I didn't get caught, no one got hurt, no harm, no foul, well, the next time, well, maybe I'll skip that step again. And at some point, all the conditions line up so you can have a catastrophic event. So what we've started doing is, thinking about our jobs, how we do work, our processes, and even the configuration of our plants to ensure that we think through what is the worst thing that can happen. And we've made modifications to address that. So just a couple of things related to safety. Wanted to move on and talk about shale gas. This is a very boring slide. I realize that. But I want you to look at the standard deviation. As you look at conventional gas, and you look at the WOBE index, and comparison to the transition between conventional shale and then straight shale. So where we're at right now with our fleet is we are in that transition stage. We may get some shale if we get the flow to reverse. However, we know that by 2017 we intend to have a shift to shale. So what are the challenges? So someone that's having to operate these assets, we are going to get shale gas. What is the impact on my fleet? On the surface, the higher WOBE looks great because it's got a higher heat content. So we have more heat, more energy producing capability per cubic foot. So that would be a good thing, except for the fact that our units are designed to control and monitor our flame for a certain amount of emissions, which we've been talking about. And when we get these fluctuations, and if you look at standard deviation there, that means that we can have lean blowouts, the units will trip, and now we've introduced a reliability issue. So what we're looking at is some controls upgrades on our units for working with the OEMs and also some third-party vendors. And in addition to addressing some issues with our WOBE index and being able to have the capabilities and to maneuver around those changes, is also look at the frequency response of our units by these controls changes. Shale also contains more ethane, which creates some additional problems for us, which could be hydrocarbon fallout. And so we'll continue to monitor the system as that occurs, but I wanted to show you just one more thing related to what we're seeing in the plants. And I wanted to make sure I could see it well up here. You know, these are the internals of a combustion turbine. And the question is it sulfur or is it pollen? So we were having an outage in the spring, you know, and if you're not from the Carolinas, there's plenty of pollen around in the spring. And the workers noticed that there was this light dusting of this yellow material on some of the parts. And of course, they all assumed it was pollen. So they continued with work, didn't mention it. And then after coming online for just a short period of time, the unit tripped off. They were in a forced outage for a week to figure out what was going on. And as they took the parts apart, they found this dusting of material. And it turned out to be sulfur. And based on some research, I've got one picture I'm going to show you. So this is a witch hat strainer off the, let's see which part. It's off the third stage, the Bravo stage off can 3. And what happens is, as you get this material buildup, you'll get a temperature flame spread across the unit. And once you get a flame spread of about 75 degrees or so, the unit will protect itself. The controls are designed to protect the unit, and it will shut down. And so that's what we saw. And based on some research that one of our engineers did, what we determined to have happened is a desublimation of sulfur. It's when the temperature of the gas is not at the highest level that it should be, and you experience some pressure drops. The sulfur basically drops out of solution. In some of our plants that are higher north, closer to some of the shale gas, you'll see some indications of over-injection of mercaptan, which shows up as more of a crystalline effect, and you can get that out through filters. So what we're doing to address this situation is we are evaluating projects to add some duplex strainers into the plants. And I do not expect you to read this, but I just wanted to throw it out there as a way to manage your business. So, you know, I've talked about a lot of different challenges, and with so many challenges, what do you focus on? And in my region, we have a strategic advantage compared to the coal fleet. Due to the age of the various coal plants, they're different manufacturers, they're different configurations, and they're just a hodgepodge. But I typically have about 2 basic designs in my fleet. And that is my strategic advantage, because whatever lesson I learn at one unit, I can apply across my entire fleet. And so that's what I'm trying to do here with this chart. And this comes from Dennis Pascal, which is a book that he wrote called Getting the Right Things Done, and it's on strategic deployment. And it's a way to look at your business and how to get the biggest bang for your buck, because we are limited on resources, yet we have to perform. And since we are trying to blend the strength of my fleet for operational performance, we target 3 different areas. We're looking at people, and we're looking at asset management, and we're looking at cost. And so I'm just going to talk to this one strategy that's up here now is on asset management. So the first thing you have to do is figure out what you're working on. What's my gap? What's my problem? So today, in today's world of coal plants, predominantly leading the way we do business, and nuke plants, we look at reliability in terms of equivalent availability, commercial availability, equivalent forced outage rate, peak equivalent forced outage rate, and start reliability. This is, everybody does it. This is benchmarkable. It's the way you do it. This is how you do business. You're in the utility industry. This is what you do. So what's our recent performance in my fleet? So I've got the metrics up here, and I'm all green. I have nothing to do in my fleet because we're meeting all our targets. I'm done. I can go home and collect my paycheck, and I'm done. But am I? So what did we do? We decided to look at it differently. So in traditional reliability metrics, we're trying to define what is important to our customer. And we can think of our customer as folks with meters on their houses, at their businesses, at their industry. But the one thing we look at is also, what does our dispatcher want? Our dispatcher wants us to be there when they call on us and to stay online. So if we were able to translate that into immediate dollars, what would it look like? And so we're all kind of familiar with the parts. We've talked about the cost impact of these combustion turbine units. And so we wanted to calculate our impact in terms of CT parts impact and replacement power. So the analysis I'm going to walk through is a little dated because there's a greater spread now in gas and coal, but I think you'll get the point. So we calculated our CT parts impact, and this is just a rule of thumb we're using, the $6,500. There's a standard number of starts you can have on a gas turbine before you go into a hot gas path or a CI. I think we're all familiar with that concept. And what we did is we calculated the life cost of those parts into the number of starts. And since combined cycles are almost base loaded, we converted that to an hour. And then we also calculated replacement power. So if I lose one of my units, what does that mean? Well, I've mentioned that we're now $9 ahead. When we did the analysis, we were just $6 ahead. So we based a calculation on replacement power if we lose the unit. And I'm referring to it now as lost opportunity. So this is a way of me diving into my business at a much deeper level than how the industry expects me to look at my business, which is E4 and start reliability. And so then I've developed a target. So I wanted to save $2.9 million this year. You won't see that on my balance sheet. You're going to see that in future years' dollars. Because what it turns into is trying to avoid trips on my units. And with every trip, I go through fewer thermal cycles, and therefore I'm going to have a cheaper operating cost over the life of the unit. So I'm going to talk to you about data. And I'm sure many of you have used GADS, have referred to GADS, but GADS is how we code all of the forced outages, D-rates, planned outages within our units. And it's not necessarily wrong, but it's not necessarily the most detailed information you can find. But we went through every single event in my fleet, every derate, every forced outage, and reclassified them to come up with what is the real cause. And in future years, we plan to use, I would say, better data, which means more manual entry. We're trying to streamline that. So the better our data, the better our results, and the better our long-term performance. But I wanted to show you a couple of things just from the analysis. And I think this will resonate with some of you, which is all the events. So in order to improve, the definition of insanity is doing the same thing over and over again, expecting a different result. You have to be honest with yourself, and you have to look at what was my performance really. At a deeper level, what was my performance? And I'm going to focus on the red items here. At 128 unplanned, undesired CT trips in the fleet. So 128. So that is about $17 million in parts impact cost. So that's pretty significant. So something to work on. The other thing we realized is we had a significant number, lost opportunity of $1.3 million in solenoid-related events. So valves. Valves, simple things, killing us. We have more DCS control-driven valves in the combined cycles than we did in the coal plants. It's a higher level of understanding of our controls. The third thing there, I've heard several people talk about the polar vortex. So the fleet experienced significant freeze issues in 2014 due to the polar vortex. And in my fleet alone, I lost every combined cycle except for one. It was a bad, bad week. If you lose every power block you have. We equated that to $2.4 million. And when you're in a polar vortex and everyone is looking at your generation, it's a bad day to have goose eggs. So, some of the lessons learned from that in 2014 were there were some gas availability issues. And so there was an idea that since we were limited on gas, let's make sure we get our steam plants on first, right? And then we'll bring the coal plants on second, or the combined cycles on second. But, we all know that combined cycles, there are two on one plant. That one is a steam plant, right? So there's steam in there, and steam and water freezes. So we had some issues. And by the time you get behind on freezing, and your heat tracing is not up to par because in your EPC to O&M transfer there, the EPC is looking at the last thing they put together sometimes is the heat tracing. And when your integration team is focused on getting that unit started, sometimes we don't look as closely at our heat tracing as we should. But those are some of our issues. And then finally, we had some human performance events. And when I say human performance, I mean human error. And that's because we had our transmission group come in, and we didn't adequately provide risk assessment over their activities to ensure that they were using proper error proofing, which is peer checking and self-checking and proper communication to ensure that they're on the right component. And we lost an entire plant at 1,800 megawatts. So that's, again, a major contributor. So when you look at all those things, you can start developing a strategy just with a simple Pareto analysis that has resulted in us using more diagnostics on our valves. We can make the business case as to why we need to invest in our freeze protection and ensure that we have everything we need there. But this is how you make that business case to senior management to ensure that you get the money you need to improve your reliability. But it's also a way for us to go out and talk to employees. Because strategy deployment is not about just sitting in the corporate headquarters and talking about what would be good to do. It's about making it hit the ground. And this is just some pie charts that we use to talk to our employees. And the one thing I would like to say is, the way this happens is you have management that analyzes the data, you have engineers provide the data, and you come up with a plan. We're going to work on our valves, we're going to improve our heat trace, but then you go out to the plants. And I had the opportunity last week to participate in what we refer to in this strategy deployment as a catch-fall situation, where we pitch the idea to the employees and they provide feedback to us. And what was most interesting to me is to watch the management, and I'm going to call it middle management, when they were telling me, we fixed it, the heat trace is fixed, and I got to see the craft. These are the guys that are in the field at sub-freezing degrees, and they're saying, no, it's not. And that's when you know that you're on the right track and you've got more work to do, and we can close the gap a little bit more. So this is how we're trying to improve our business in my region. So I'll open that up to questions.
Any questions?
Just curious, when you had the sulfur issue, what levels of sulfur were you looking at?
You say what levels of sulfur?
Yeah, I tend to think of sulfur in grams per 100 cubic feet or something like that.
This was like a dusting. I've got some measurements in the back and from what we saw at another plant from the Midwest, but I can't give you the size off the top of my head.
How often do you take the opportunity to sit down and just have a chat with marketing and folks on how they're doing, what's working, what's not, at their plants?
I don't have bargaining unit within my group.
Okay, so you're non-union?
No.
I was wondering about you said you valued your standardized design.
Mm-hmm.
How do you put numbers on that compared to latest, greatest, best? The next generation, this is more efficient, whatever.
It would look at, obviously, heat rate, so we would have to construct the next cheapest energy that we can construct, so that plays into it being a regulated utility. But from operating fleet, I mainly have the GE 7Fs and I have Siemens 501s, and so that is my strategic advantage. I'm playing the hand I've been dealt.
Would you care to delve a little bit more into the shale gas impacts and how do you know what you're receiving? When you're having these transition issues between the Carolinas gas and shale gas, you have calorific monitoring, and how do you know what's getting down that pipeline?
I get a call from that guy sitting right there. That's usually how we know as to when we're going to get impacted from shale gas. The issues we had at Lee, where we had the desublimation of the sulfur, was related to we didn't have our gas heaters in operation, and even though you may think you don't need them, you need to have them turned on. But we haven't had an issue in GE units without a gas heater. You will see it in our Siemens units.
Are there any operational steps you have in your procedures or operating procedures that you change when you're going to fire this shale gas at a specific quantity, or
no? Because
the heat rate was changed pretty significantly.
Yeah, but the controls will all take care of that.
Okay, so that's designed in.
That's right, and We are upgrading our units right now, so the units that are most likely to receive shale gas first because of where they're located already have the auto-tune installed, so they're less susceptible, and we're moving in that direction. We'll either go with the OEM or a third party, so that will help us from a control standpoint.
And the other thing, in that specific example, the actual pipe is able to, because there's multiple loops in the area, they're able to actually troglodyze more ideal gas stream. If we need it. Doesn't work every time, but they have a little more flexibility.
Julie, you said you have both GE and Siemens machines. Do you have long-term service agreements with those two companies for the machines, or do you do your own maintenance?
Only one.
Only one.
Mm-hmm.
So can you talk about comparing doing your own maintenance work with a service agreement and how that relates?
So we are very new into the LTSA, so just approaching CIs right now because of the age of the units. It's a matter of your inventory that you would have to carry. I mean, those are impact. You have to look at it from your business standpoint as to how much inventory you're going to carry. Do you have the skill set to conduct your outages and the resources? You know, one of the things that we do is our craft, our maintenance services group that conduct the outages, they service our nuclear plants, they service our coal plants, and the gas plants. So will you have enough resources to pull off all those outages? I mean, you have to make that business decision. And I will say, if you're going to have those negotiations, they need to be occurring when you're doing your offers to purchase, not afterwards.
Any other questions?
I had one more question. Manpower for the mine cycle, 600 megawatt. What kind of resources do you have in a site like that? Do you have it broken down?
Off the top of my head, there's a 3-on-1 that's about between 950 megawatts, and it can hit about 1035 in the winter. We have about 43 resources there.
How is that supported from an engineering? Or do you have a centralized engineering that support that?
There are engineers on site that provide support, but in addition to that, there are central engineering resources that we can call upon if needed.
All right, Mike Hale, principal engineer at Southern Power.